My name is Samantha George, metric number 183443. My final year project is titled Templating of Bioactive Glass using Cellulose Nanofibers for Bone Scaffold Application. The project is supervised by Dr. Dayang Radia binti Awang Biak. Issues pertaining to the conventional treatments for bone repair and regeneration lead to the demand for new bone regeneration treatment, like bone scaffolds. Bone scaffolds are defined by materials that provide mechanical and functional support for bone regeneration. The most common material that is used for bone scaffold is bioactive glass. Bioactive glass needs to have high porosity so that cell penetration, oxygen and nutrient exchange can occur, and it can support the functionality of the bone tissues. Problem statement. A common issue that occurs as a result from using synthetic bone scaffold is the formation of tissue on the outer edge, which would limit the cell penetration, oxygen, and nutrient exchange. One method to prevent the occurrence of this is through the incorporation of macro or micro channels within the scaffolds. The channels will be introduced by introducing a template in the bioglass matrix. The template increases the porosity of the particles. CNF with high wettability, excellent roughness, and large surface area was selected to be the template for the bioactive glass particle. Another issue related to bioactive glass scaffolds is the biodegradability that is affected because of high temperatures during sintering process. High temperatures can cause some components of bioactive glass to be degraded. Therefore, the effects of the sintering process must be evaluated, especially regarding the chemical properties, morphology, and crystallinity of the particles. The main objective to improve the porosity of bioactive glass via templating method. The research objectives are divided into two: to synthesize bioactive glass via sol gel method and to synthesize bioactive glass with cellulose nanofiber as a template. The parameters that would be varied are the sintering temperature as well as the ratio of CNF to bioactive glass. For the literature review, bioactive glass was discovered by Hench and has been proven to have strong interfacial bonding with the bone. Templating has been used for fabricating by Chan et al. As well as Dong et al. The properties of nanocomposites allow increased protein absorption, nutrient exchange, and porosity compared to macro-scale biomaterial. Now for the method. For the first objective, the synthesis of bioactive glass using sol gel method. For the step 1, 1 mole of aqueous nitric acid solution was prepared. After stirring for 60 minutes, tetraethyl autosilicate and triethyl phosphate were dropped into the sol dropwise. After dissolution, sodium nitrate and calcium nitrate powders were added into the solution. After 45 minutes of stirring with a magnetic stirrer, a clear homogeneous solution was obtained. The homogeneous solution was then placed in a Teflon container for aging for 7 days to allow the sol to transform to gel. After heating it at 70 degrees Celsius, the gel was then aged in an oven and dried at 120 degrees Celsius. After the furnace heating, which allows the gel to transform to glass, it becomes powder. It becomes bioactive glass powder. For the first objective, what was observed was the effect of sintering on bioactive glass. This was done by observing the bioactive glass before and after the bioactive glass was heated in a furnace at 750 degrees Celsius. The samples analyzed are as shown. The bioactive glass was synthesized and then it was compared with commercial 45S5 bioactive glass and pure CNF. The analyses that were conducted were SEM, scanning electron microscope analysis, FTIR, XRD, as well as EDX and BT, but only for the bioactive glass that was sintered at 750 degrees Celsius. For the second objective, the steps are similar, except for the extra step of adding the CNF template after 45 minutes of stirring. Once a clear homogeneous solution is obtained, the steps are followed through as per objective 1. For objective 2, the sintering temperature effect was observed by using 5% CNF sample. The temperature was varied between two temperatures of either 550 degrees Celsius or 750 degrees Celsius. The samples were analyzed. Bioactive glass with 5% CNF were observed before the sintering process, after sintering at 550 degrees Celsius, and after the sintering temperature of 750 degrees Celsius. As for the next parameter, which is the CNF content in the bioactive glass, using the formula as shown, the CNF concentration were varied according to the volume of the suspension. The samples prepared were bioactive glass with CNF content of 10 to 25% of CNF. The analyses that were conducted on the bioactive glass were morphology analysis, chemical properties analysis, crystallinity analysis, composition analysis, and porosity analysis. For results and discussion, for the first objective, which is to observe the effect of sintering on bioactive, the samples were prepared as shown. For the morphology, according to the magnification view, two magnifications were used, which is 300 and 3000. At 300, the bioactive glass before sintering was observed to be agglutinated, and at higher magnification was observed to still be gel-like, as opposed to the bioactive glass at 750 degrees Celsius. When compared with the commercial bioactive glass, it was seen that the bioactive glass at 750 degrees Celsius had a more porous surface and less dense compared to the bioactive glass that was commercially produced. According to the FTIR analysis, it was seen that the bioactive glass produced by a sol-gel method at 750 degrees Celsius had the same pattern and same chemical functional groups as the bioactive glass commercially produced. According to the XRD analysis of the three molecules, it was found that bioactive glass with sintering temperature of 750 degrees Celsius had the highest crystallinity compared to bioactive glass before sintering and commercial bioactive glass, which was found to be amorphous. As for the second objective, the first parameter observed was the effect of sintering process. The samples were prepared as shown. The bioactive glass with 5% of CNF before it was put into the sintering process was seen to look more wet. However, there were no detectable observable differences between the bioactive glass at 550 degrees Celsius as well as the bioactive class at 750 degrees Celsius. As for the morphology of the particles, it was observed that at 300 magnification, it was observed that the bioactive class at 550 degrees Celsius still had more agglutination compared to the bioactive class at 750 degrees Celsius. As with closer observation, it can be observed that the bioactive class at 550 degrees Celsius did not cover the CNF molecules properly, and it was also observed that the molecules were still gel-ish. It did not look crystalline at all. Next, for the FTIR analysis, it was observed that the bioglass at 550 degrees Celsius had similar significant functional groups to the bioactive glass at 750 degrees Celsius, but it did not have the same spectrum trend as compared to the other molecules, which is the bioactive glass at 5% CNF concentration at 750 degrees Celsius, bioactive glass at 750 degrees Celsius, as well as the commercial bioactive glass. Next, for the XRD analysis of the bioactive glass with 5% CNF, it was observed that the bioactive glass at 750 had the highest crystallinity compared to the rest of the molecules. As for the effect of CNF content under the second objective, we observed that there were no detectable differences among all of the prepared samples. Secondly, for the morphology, it was observed that at 0 CNF content, there were lesser particles dispersion compared to 10% CNF, where it had the highest dispersion. However, at 15% to 25%, it was observed that there were more CNF compared to bioactive glass, and there wasn't an equilibrium of particles. On closer magnification of 3000, it was observed that 10% had the best architecture, where it took the shape of the CNF particles as opposed to the rest of the percentages of CNF. Next, for the FTIR analysis, it was observed that the addition of CNF does not affect the trend of the spectrum. Furthermore, it was observed that all of the molecules had the same trend and there was no observable differences. Next, for the XRD analysis, it was observed that bioactive glass with 10% CNF had the highest crystallinity compared to the rest of them. For the EDX analysis, it was observed that after the addition of 10% CNF, the molecules still had similar composition of silicon dioxide, phosphate, calcium oxide, as well as sodium dioxide, which is good because the composition was not affected by the CNF. As for the BET analysis, it was found that with bioactive glass with 10% CNF added had a 15% higher pore size, which proves that CNF increases porosity. Bioactive glass with 10% added CNF had lower total surface area, which corresponds with the macromolecule form due to its attachment to the CNF molecules. Usually, specific surface area of bioactive glass produced by a sol gel method should be around 100 to 300 meters squared per gram. However, the BET surface area that was observed was only 4.864 meters squared. This could be explained by the absence of hydrofluoric acid or stronger acids, which can help the bioactive glass to dissociate more. Next, for the conclusions, it was found that the sintering process is necessary for production of crystalline bioactive glass. The optimal sintering temperature for bioactive glass synthesis is 750 degrees Celsius, and the best concentration for CNF to be used for templating is 10% by mass of CNF. Furthermore, it was also conclusive that the addition of CNF does not affect the chemical properties and composition of bioactive glass, but reduces the average particle size of bioactive glass and increases the pore size by 15%. Therefore, in conclusion, it can be concluded that the templating method using CNF improved the porosity of bioactive glass. For the recommendations, mechanical strength of bioactive glass should be studied. The in vitro study should be carried out to observe whether CNF affects the formation of hydroxyapatite in simulated body fluid. And finally, in vivo methods should be used to study the effects of CNF addition in bioactive. That's all for this project presentation. Thank you.